Welcome to the ML in Production Reading Group's meeting to discuss Chapter 9 of Chipwin's Designing Machine Learning Systems on continual learning and testing in production. So, the general idea with continual learning is that we want to update our models regularly. This is something that is maybe the furthest or one of the biggest gaps between research style machine learning and production style machine learning. This is it's not necessarily the case that everybody doing ML in production has to do continual learning or is currently doing continual learning, but that is changing as people build more and better tools for it. And this is not something that's really on the radar, I think, of a lot of academics. So there's a section at the beginning sort of talking about why you would want to do continual learning and why it's so hard. And then this kind of graded four-step process that takes you from that sort of charts how an organization might go from doing the kind of classic thing of just every once in a while retraining your models all the way up to full on continual learning where models never stop learning from data in production. And then one of the biggest challenges of continual learning, and that has come up sort of over and over again as we've touched on continual learning in previous chapters, has been how do you know that you aren't breaking your model? How do you know that the model is actually better? And the kind of answer put out in this chapter is that you've got to test it in production, which is a little bit wild and maybe contrary to the way a lot of people think about testing. It definitely, the first couple times I saw it, I kind of recoiled in horror. But testing in production is actually with systems that have components that are really not under your control, like user data. There's not much you can do besides test it in the production environment. And so the key thing is knowing how to do that safely, knowing how to marry the benefits of quality assurance um, and of like software stability that you get from testing with from like classic style testing with the realism of deploying something in production. So I thought that was kind of an interesting, a little bit unintuitive for me, I guess, but a really interesting way of describing how to do continual learning that looks pretty different for machine learning than it does for lots of the other types of software that people who do machine learning research are maybe used to working on, like open source Python libraries don't really do this test in production thing. All right, so that's my overview of this chapter, of its contents. Does anybody have any a particular section that they really want to drill down on? We can go through it in order if there's nothing anybody wants to particularly highlight.
So, a question I have, I don't know if you can answer this. So, I'm really interested in federated learning, and I know that for federated learning, I was reading this paper by Brendan McMahon that was like a survey on federated learning that talked about how you do need to actually monitor your model in production. And I was wondering if this is how you would monitor your model in production, or if this is not how you would do that.
Yeah, that's interesting. Actually, if you would mind sharing that paper that you just mentioned in the Discord channel, I'd love to see it. I don't I haven't thought or worked much in federated learning, so I can't give you too much specific stuff, but that paper would be a great reference to take a look at. Uh,
Oh, I really, yeah, I love federated learning. So yeah, I can share that.
yeah, I'd say that federated learning and continual learning do share certain challenges, which is people have started to talk about basically adversarial attacks that you can do by feeding data into neural networks, getting them to misclassify other data points or sort of like inserting a secret key in a way that looks like very kind of like steganography or other kinds of forms of cryptographic communication where you can like get a model to behave differently if you change bits with low significance. Federated learning is where a lot of that work on adversarial attacking has come on attacks via data poisoning, I think is one term people use. And this is also going to be a problem with continual learning because now you are allowing what your users are sending you to go into your model. So there's maybe a little bit more control in this setting than in the typical federated learning setting. Or in the federated learning setting, users send you gradient updates rather than sending you data. And I think there's more attacks are possible, but I think they share some of those same issues, even though the settings have big differences with continual learning being much more centralized. Let's do the normal thing and kind of step through the chapter and maybe pick out highlights or things that we're interested in. Continual learning usually doesn't mean the training paradigm where a model updates itself with every incoming sample. That's on, like, people used to call that online learning, online SGD. If you look at old NeurIPS papers, you might see that kind of thing. But that's not a thing people do much anymore, in part because we really only are able to achieve the scale that we've currently achieved by doing parallelization across batches. And so updating on single instances is not something that's really feasible. And so people tend to like collect up data before training new models. And there's this like sort of collection process, often with a delay in order to get hold of a hold of new labels. So that's the kind of continual learning that we're doing, and maybe it looks a little bit different from the kind of lifelong learning of an organism, of a human or an animal. And the paradigm that Chip puts forward for training models is stateful training as opposed to stateless retraining. A lot of people try and retrain their models from scratch on data. So when they need a new model, they go all the way back to random initialization and train a model from there. That's helpful, as she points out, if you need to do things like completely change around architectural features of your model, add more layers, remove some layers, put in batch norm. If you're doing that kind of model iteration, you don't have much choice. But this stateful training, which is basically pull the model, uh, basically freeze the model at the end of training, keep in PyTorch, it'd be the like state dict. Keep the dictionary of the state of every aspect of the model at the end of training. And then when you need to update your model, sort of unfreeze it, take it out of cryogenic stasis, and train it on new on the latest incoming data. And that gets you sort of like a lineage of updated models from that base model. Um, and those models can update with time. You can on a schedule or on the basis of triggers that tell you when you need to retrain your model. Right. So this is beneficial in that you're updating your model with less data. Um, it Training a model from scratch is going to require a lot more data than fine tuning the same model. Um, and so like that's expensive in a large organization to like just getting all the data together is going to be hard. Like that big training data set and maintaining that over time is going to be hard. I think in a previous chapter, she mentioned that stateful training, maybe that was this chapter, in stateful training, you don't actually have to preserve the data over time. So if for regulatory reasons, you need to delete a bunch of user data that was used in your training process, you can do that if you're doing stateful training, but you can't do that with stateless retraining because you would need that data in that batch. In at least some versions of stateful training. And there's
Oh, sure. Can you go
yeah.
to the grub hub? Or
Oh yeah.
you go to the couple. I had a little gripe with this one where it says grub hub. They use stateful training to allow models to merge faster and require less compute power. And they got 45 times less. They reduced their training compute by 45 times and increased their purchase rate through it by 20%.
Hmm.
I understand the less compute power, but I don't know if that increased by 20% is like a function of the amount of data they have. And it's just like their experiment, they got that because maybe they didn't have enough total data or something. Kind of, I wasn't expecting them to get a better purchase through rate by stateful training.
I didn't read that, so I can't give a super informed response there. I guess I would say that yeah, there's no guarantee if you're doing it on the same cadence, stateless retraining and stateful training, it's not obvious to me why you would get substantially different models. It maybe your stateless retraining was literally only on that day's data. And so being able to take into account more historical data is like by the
Okay.
fact that it's incorporated into the model is useful.
Yeah, okay. Now that you say that, maybe it's because their most recent data, the fresher data, is better than the earlier data. Like the earlier data hurts the performance more than just a fresher set of data. Okay. Right. Maybe that's the reason. Thanks.
Yeah, this online learning for recommendations at Grubhub is a paper that I see cited by folks in the ML production, ML ops kind of world. And like people talk about it quite a bit. So I would definitely, yeah, I should definitely check that out. And I recommend other folks read it. Maybe we can do that in the future reading group.
So also, I think you point out this, you know, essentially like freezing of the layers and only updating certain layer, like the head or like two or three uh, output adjacent layers. I think, this becomes like, I mean, especially in NLP, like often it, like the recommendation now or like something that seems to work generally is like just unfreeze all layer. Like we had all this phase of like, of like layer wise doing things and like rather than freezing. But I think like, oh, like, at least in a lot of NLP stuff, it's becoming like, if you have like a few thousand or a few tens of thousands, data points, sufficient data points, just unfreeze all there. And it typically works better. And so, but, I think this still brings up this thing of some, this is a hyperparameter in
Yeah.
itself, which you have to kind of tune for your problem. And so, for instance, like I've been in this situation where, I mean, essentially, like, where we had to like we had one base model and and we had one model per customer essentially. And so every time, there would be lots of, so we'd have lots of eventual fine-tuned models deployed in production. And there again, like we had to experimentally figure out, because when we get a new customer, there would be a phase, there would be up to some time when we want to not unfreeze the whole network. And eventually, at some point, we would want to unfreeze the whole network, and which is what would give us the best performance. And so, yeah, I mean, there's a lot of like, I don't know, experimentation and trial and error to kind of figure out these hypotheses.
Yeah. Yeah, that's interesting. Yeah, I guess, yeah, my bias, I really like how clean the idea is of having centralized, like a single backbone that has lots and lots of heads trained off of it. But yeah, you are right that people have found that you can sometimes get much better performance by unfreezing all of the weights. But it does, again, as you pointed out, bring you a lot of additional complexity, both like cost in terms of having to work with all those parameters, and then now this hyperparameter of how to do your unfreezing and when. Interesting to hear. So that was so you're saying that was like a really important hyperparameter, basically, what like when the model, the like backbone was frozen and not frozen.
Yeah, because I mean, so it was, and I mean, it was an automation use case where essentially like we were, and that actually, okay, so I'll get to that later. But and so it mattered that we get the most at each point, because that would determine how much manual effort needed to be put in. And so this schedule was important, because otherwise, we would, we would not be able to get the most automation that we could. And so it mattered.
Got it.
Plus another thing though, which I wanted to say overall, really like maybe in this chapter, but also in general, like there is a bias towards, I would say, B2C use cases, which is like what, maybe, I don't know, 50 companies in the world are that big B2C companies, and there are lots of B2B companies who are trying to build, ML model production. I feel like, yeah, there's not as much covered. So like automation is one very common case I've seen. Like just
Hmm.
automating some process, some other process, and there's other process challenges which come up, which I think, it's not as much covered. I feel.
Yeah, I think that's fair. I think it is very much oriented towards that kind of business business to consumer. like lots and lots of users who are basically, yeah, who are, people off the street, not, not people from a particular industry or working, and not companies. And it also, like, from my perspective, it also is not focused on the kind of machine learning that's oriented at building like a fundamental new piece of technology that's like not consumer facing. But I think the reason for the bias is, I guess, at least in the US, in California, in Northern California, where this book was written and developed, that's the use case where people have done the most sophisticated ML in production. And so if you go out and ask people, what does your ML in production, what do your ML in production problems look like? You're going to get a bunch of like big social media and like user oriented, public user oriented tech companies talking about those kinds of problems. Yeah. So keeping going, in the chapter, uh, so I think there's a section on why continual learning. I think there were maybe some questions or clarifications here. Yeah, this question was about yeah, what about this Black Friday example? So the Black Friday example um is, I think the basic point here is that throughout the day on Black Friday, Amazon customers are going to behave very differently than they behaved in the past, and even than they behaved on previous Black Fridays. So on this day, like, you're getting 100x as much user behavior, and so things are changing. Um, like, even if you assume that things are stationary throughout the day, like, you're getting you need to like retrain within that day in order to learn from the morning and handle the evening. But then it's also the case that maybe things are even changing throughout the day. There's so much happening on the website throughout that day that there's meaningful differences between what happens in the morning and what happens in the evening. Um, and so it's this is the kind of case where you really actually do want um, like really close to like real time machine learning to discover that the hot product this year is like Baby Yoda dolls, or that, and that people who buy those Baby Yoda dolls also buy like glasses that say "Don't talk to me till I've had my wine" or whatever. So like that kind of uh, like that can mean correctly recommending those things within the day of Black Friday can mean like millions of dollars of additional revenue for a place like Amazon. And so I think that's what that example was trying to get at. I don't know if anybody has any comments on that, or wants to put a different perspective. Oh, what's the alternative to learning throughout the day with fresh data? Um, I think, like, I guess the alternative is just having your models like be frozen in place the whole day, right? They just continue to recommend people the products that you would recommend based off of historical data. So if somebody buys a flat screen TV on Black Friday, you recommend them other flat screen TVs because that's what's worked on other days. Um, and so, like, that probably works fine. It's just that even a few percentage points, or a few tenths of percentage points of increase in recommendation quality on a day like Black Friday um, can mean millions of dollars. And so it's worth expending hundreds of thousands of dollars on engineering power and computing power to make that happen.
I guess I had a comment on this section, but the couple questions about the rare event or the Black Friday shopping. And it's the page you're talking about. Uh, I haven't looked into it, but I've ever remember looking at some people making stock algorithms, and I don't know how true it is or not, but the notion was that sometimes you do get the similar event where there's like extreme spikes or whatever, and sometimes it's just like normal as predicted from a normal model. And one thing someone was suggesting is they have a model that predicts what the general situation is. Is it
Mm,
like in your example, in your highlight, say, is it a big event in the top line? Is it a big event or ride demand surges? Maybe there's like some big event. You have this general model that says, okay, it's not a normal time. It's a, there's some event happening in this location. Let's switch to this. And then they have like two different options. They have like a quick demand, like that can react fast model. And then they have like a general model. And then they'll point to which model to use because there's not enough data to, or they haven't figured out how to make one model that can do everything.
yeah.
They have two models instead, or multiple models.
There's different ways to design this, right? Because
Yeah.
you can have literally hundreds of models doing the filtering, and
Right.
then one model do the re-ranking at the end, and you only just have to retrain the or continually learning the re-ranking model, since that's the most up to date, and then you can have your sparse model, maybe yearly model doing the filtering, so you have different sources of filters of recommended products, and then you do a re-ranking at the end to decide what actually to serve. So you don't have to have models like choosing between one or the other models. You can have a lot of models and then re-rank at the end.
Mm, mm, interesting.
And I think one of the reason this is like online learning is useful for this type of event is that there's no data. Basically, you the data you have for example last year or the year before or like 3 years ago is pretty much irrelevant to the Black Friday event. um, and perhaps since nowadays people have events leading up to events, right? Like you have like the pre Black Friday, post Black Friday, and then online Monday, Cyber Monday, whatever. So you can still use the recent week's data, and then perhaps different email campaign data that you sent out as part of the training data to determine how much of an impact you can get. But yet, but either way, yeah.
Yeah, there are many architectural potential solutions to this problem, and continual learning is maybe just one of them. There's this nice section here on continual learning challenges, and I think the biggest ones are come from the way data works in enterprises, which is to say that like if it's user data coming from an app, like that data is there's like a gigantic system built around like processing and using that data to run the application. And that's like the province of site reliability engineers and data engineers who have nothing to do basically with the machine learning um, any machine learning aspects of the app or the business. And so there's the previous way that was handled was this stuff would maybe get pulled, like would get eventually like daily, weekly, monthly, even put into some place outside of the main application, the data warehouse or some other like um data storage layer, and that was like the firewall between the application and business intelligence, data science, and machine learning. But if you do continual learning, you break that firewall. Um, and so you need basically data to be coming in real time from the user behavior in the application. And so you need to get a step closer to the actual operating application. And tools like Kafka and Kinesis are these kinds of streaming data transport tools that are increasingly used in the operation of large applications that also work decently well for doing like rapidly streaming data to your machine learning model. So this is if you're interested in continual learning at an enterprise or in a large ML team, this is going to be one of the like difficult sticking points. I think Aman mentioned that in one comment, like, yeah, there's this huge infrastructural upfront cost that you have to pay to get this working before you can do any continual learning. And so before you will actually realize or see any of the promised benefits of continual learning. We've talked about labeling quite a bit in the past. It came up as early as the data chapter, which is like chapter 2 or 3, and we keep coming back to it. When you're doing continual learning, you need to be continually getting a hold of teaching signal for your network. And so that means some kind of label in most cases. And that and continual learning is, hard mode for this kind of thing. You need to be able to get these labels quickly and combine them with the data quickly and cleanly. And uh, I guess my one contribution on top of the stuff that Chip says is to be careful that you don't cut too many corners in the process of trying to get your natural labels quickly. Remember that whatever you're choosing as your labels are, that's what your model is going to optimize for. So if you decide that that in order to get quick retraining, you're going to count it as a successful recommendation if the user clicks on it within 30 seconds, then you are optimizing for things users will click on within 30 seconds. And maybe that's right for your use case. Maybe it's not. And we've talked about lots of examples where various choices of quote unquote natural label gets you a system that doesn't optimize what you really want it to optimize. Right. And this ties back into choices about the design of that real time transport system. If the real time transport system can only get you data within a certain time window, then that's the only thing that's the only time window of user behavior you can optimize for. So this ends up like touching on top level business goals, machine learning, like optimization and data construction, and then also infrastructural concerns about the design of the data intensive components of your application. Maybe we could just quickly go over these 4 stages of continual learning for 5 or 6 minutes before we go on to the testing in production. The 4 stages of continual learning start off with something that looks a lot like the way machine learning research goes. Build a data set or find a data set, train a model on it, and then maybe at some future point, just like start over, train again. Do it manually, do it ad hoc. And then lots of features of this pipeline are often super manual, constructing the data set, aligning the data set with the model, training the model, getting that model into a place where it can be deployed, and deploying that model. All of that stuff can be and often is completely manual. And maybe unsurprisingly, because lots of pieces of software delivery are often manual, especially at the beginning. Anybody who's ever tried to fully automate the distribution of a Python package knows how painful it can be to try and automate something like this. That ops skill set is a tough one. And automated retraining is the first step away from that, of at least automating the process by which the model is retrained and doing that on some kind of gut feeling once a day, once a week, at night when we have but like leftover Slack computing power. And you need to automate a bunch of this stuff that is likely semi-automated or not automated at all in your existing pipeline. So getting data, running the training process, evaluating the model and deciding whether it's deployable or not, and deploying it, all this stuff. I think we'll talk a little bit about scheduling and orchestration for this with these like pipeline management tools like Airflow. That's the like basic toolkit for solving these problems.
I mean, the step 2 of downsample or upsample data. This is another thing which, at least for me, like I haven't figured out a good way of doing it. Again, it's another sort of experiment and figure out for a particular problem in the state that I'm in. But I was wondering if there's any thoughts on, some, I mean, if not principles, some like good heuristic ways of doing it. Because especially when you are I mean, when you're doing continual training, then this would determine how much you have adapted to the new data versus how much of the old data stuff still kind of your model still kind of responds to. And so any any ways of thinking about this problem?
I think I think this is a data problem, not a model training problem, right? So I think the cases where continual training matters, what helps a lot is the data recency problem where the most recent data is highly relevant to your current use case. But if you don't have if your data that you're dealing with doesn't have the recency benefit, then continual training is going to degrade your model by a whole lot if it's statefully trained. Let's say, for example, I think there was just a paper that says if you do transfer learning on BERT type of models, you will lose you will degrade your model by a whole lot if you do transfer learning on on a different data set.
Right.
Uh,
In ITR, I think.
Right. And so because like when you continue to train, you are basically oversampled, right? Because if you froze whatever you have already learned, the huge corpus of data, and then you are continually training, basically you are oversampling the most recent data sets, the most recent data that you are doing the safer training on. Right. So you oversample that side, and which means whatever data the model was, like the original model or the baseline the trunk model, that the data for there is going to degrade. So like if you don't have data recency benefit, or you don't have much data recency benefit, then there's not much reason to do like a stateful retraining or stateful training, right? So I think that's why I think the paper the Grubhub paper, they did an experiment on no retraining weekly and monthly retraining to compare the performance differences. But as just like 2 pennies.
That makes sense. But I mean, let's say, let's say if you do have a recency benefit, but I mean, you were doing stateful training because it, like you start with, let's say, small amount of data, and now this is going to grow. Um, so, okay, I'm again, like, let me give context. So, like, again, like the kind of automation you see there was talking about where there is like, let's say, a base model which is trained on, let's say, like 20 data sets collected across 20 different B2B customers, and now we are acquiring new customers. Okay. And now we want this model to adapt to this new customer data as soon as possible. Now you start with the stateful thing because that lets you adapt fast. But at the same time, you don't so that's for the hyperparameter thing that I talked about. Like, we have to like freeze something, at least initially, till we got like, say, 20,000, 30,000 samples, and then we would unfreeze the whole thing. But I mean, okay, so the issue is that, like, even when you are doing, this continual learning, like for the like, let's say you do it up the same patches of every 5,000 examples. So let's say that's the kind of schedule that you have. Like, I don't want it to completely overfit to the 5,000 too, right? And because, like, for the next 5,000, it's not as if like my past 200,000 examples are not relevant. It's just that these 5,000 is more relevant. And so that just becomes that sort of that balancing act where how do I balance between how much I'm going to learn from the new 5,000 that I've just sort of gotten tagged by my taggers, and this old 200,000, which is not exactly relevant, but like in a general sense, it helps, which is why I kind of started with that model rather than starting with that. So,
I mean, I think that goes well into why we test in production. Just YOLO and A/B test it to see like what's the what time frame, like what's the look back period that we should increase the weights on, right? Like even if you train XGBoost models, you can assign a weight to every different sample, right? So like you can assign a weight, let's say for example, you can increase the weight for the samples on the past month versus the past year. Right? So you can tune that, and that's I think that's going to be very different and case by case. That's going to be very different on a case by case. And
No,
use
I think, yeah, the
this in
test
there.
in production thing is, yeah, definitely something, which I thought was interesting because, I would kind of not test in production. Like I would I would still do batch wise tests. I wouldn't it just, yeah, it didn't even occur to me that I could actually do that.
Yeah. Let's jump to that section. I think it's important. There is like a YOLO attitude to testing in production, which is like, just go get put stuff out there to see what happens. But I do want to say that it is important that your testing in production is kind of graded, that you are going to get out there and the model's going to see stuff that is happening in real time on actual user or customer behavior and data. But the first step in this, and that's like a very, very important first step, is this like shadow deployment, right? Which is that you have the model basically operate in parallel with an existing model that you believe is good enough. And you compare the behavior between those two to make sure that you haven't like completely broken stuff. So your existing model provides kind of like a baseline. You might also shadow deploy alongside other baselines, like linear regression baseline or like a random baseline or whatever. But you do this in order to like prevent certain kinds of like catastrophic failure. And I think it is important to include those kinds of safety checks before you fully put the model out into production, as opposed to fully just like, oh yeah, just like push it and just be ready to like pull it back if things break. It's a little more sophisticated than that. And there are other software disciplines that are ahead of machine learning in terms of doing this kind of testing in production. I linked to a Launch Darkly blog post. They have a bunch of tools for doing this with systems like databases and like other kinds of data intensive applications where it is really hard. Just like with machine learning, it's really hard to like create a testing environment that really mimics what production is like. And there they really emphasize you still need traditional testing and quality assurance. You still need to do the things that you do to evaluate your model that we've been talking about, like subgroup analysis and checking against past known examples, checking for failure modes on particular really important examples. Still keep all of that and do like a kind of cautious first step of shadow deployment, canary deployment, and A/B testing. And then you will get greater stability out of testing in production. If you just throw out all your previous testing and immediately go to testing in production, you won't see the benefit of increased stability and increased velocity. So I talked about shadow deployment already, common in other parts of software development, maybe less common in machine learning. A/B testing is getting more common, especially actually in other aspects like user experience and user interface design. At large companies often involves A/B testing and actually trying to demonstrate that your user interface change, your user experience change is actually beneficial. Twitter is like a very aggressive ABN tester. Basically, every user gets put into a different bucket and assigned to various experiments at all times. So this A/B testing is used very thoroughly by these large companies. Yeah, they mentioned 10,000 A/B tests annually at Microsoft and Google in 2017. I would imagine that number has only continued to increase. So this is both a place where ML engineering teams will touch other aspects of the app design, because A/B testing is often like under a data science or machine learning engineering team's purview. And it's also something we can apply to our own models. I saw there were some comments here. Any thoughts and comments on A/B testing for machine learning experiments or machine learning models?
I had a question. Where says that the cases when one model's prediction might affect another model's prediction, and in which case, like I would guess, like you might have to retrain both of them and then maybe A/B test them together. Uh, or am I missing something?
Yeah, hold on. Let me read this to be super clear. Like when I first read this, what I was thinking of is you have like if one model's behavior changes things about user behavior, other models other models might need to be might be impacted. And so you can't A/B test um you can't A/B test the different models at the same. No, it's not saying that you can't do your dynamic pricing at the same time as your available driver and rider prediction. Hmm.
So I think for this case, you're gonna need you got to make sure your vet is when in the paragraph you gotta run the experiment on on similar events, but let's just say dynamic pricing and during rush hour on a Monday. So maybe in the first Monday, the next Monday are not any different. Not a holiday is the same and statistically the same. So you just have to make sure your event uh, is the same when you run both experiments. And that's why in the last line it says you might want to serve model A one day and then serve model B the next day. But those 2 days or those two events should be similar enough that you can run this experiment. And you have to just figure out how to where the boundaries are to what that experiment are.
Yeah, I think it's uh maybe the example is not clear enough, but like the problem with A/B testing is you really, really, really have to make sure that you're A/B testing on one single difference.
Yeah.
And because in large enough systems, there could be multiple like tons of different experiments that people are running or different and some of them might so you might think that you're just changing this model at this time period, but then if you don't pay attention to the surrounding system, they are actually it could not be like you might not have the exact control, so to speak. You might be like there might be other I guess covariate effect that you haven't touched. So it's just it's not easy to run A/B test.
Yeah. Yeah. So I think, jumping off of what Han said, if you're doing A/B testing and what you're doing is sending a fraction of predictions to model B while model A is still running, the thing you're testing is what happens when I add model B on top of model A, right? Rather than what does my system look like when I replace model A with model B? And that's the actual thing that you want to test. And so I think that's what this example is referring to, that you want to actually test what happens when model B is in production. And that's not always the same as model D operating on some fraction of production. And I think just generally, this is causal inference, basically, is what people are trying to do here. And like causal inference in complex systems is really, really hard. And you should probably have data science and statistical experts to help you with the design and setup of these kinds of experiments.
Right. So, I mean, it's not like model A and model B. I mean, it's not like model needs model A's predictions to be trained. It is more like, it's like a complex system. And so, got it. So you want to change, like, you want to A/B test two states of the complex system overall rather than, got it.
Yeah, and what you're doing instead is creating a superposition of two pure states of 90% model A and 10% model B, and you're testing that against your pure model A. Yeah, great question, Aman. Yeah, I definitely did not fully grok that example before that discussion. So thanks all. Right, so there's lots of stuff here about this kind of testing stuff. I think this is a place where traditional statistics is very helpful. Oh, comment here from Aman. Yeah, so even if the result is statistically significant, it's possible that if we run the experiment again, we'll pick another model. Right, which is just a matter of like statistics can never fully get rid of randomness. There's, always a chance your statistical inferences are incorrect. The one thing that I wanted to bring from my like background in stats is it's like effect size is something you should always keep in mind when you're doing your A/B tests. You should try and calculate how big of a difference it is, not just whether the difference is statistically significant. This is like a very common mistake that people who just learned hypothesis testing kind of fall into. Um, they over index on whether something is significant or not, and they present all of their results in terms of significance. And this like drives me up the wall actually with a lot of the way that biological research is presented. Rather than quantifying how big the difference is between the groups, they just say the difference was significant, p less than 0.05, p less than 0.01, and don't give a number. But with this A/B testing, there usually is some metric that we care about. Accuracy change is maybe simpler, or user engagement is maybe simpler. You'd love for it to actually be revenue impact or whatever high level business goal. That's not always possible, but when it is possible, that's the gold standard. And if you do bootstrapping, for example, like randomly redraw from the model's predictions over a period of time and use that to give yourself some sense of the variability in your effect size estimate. And that gives you, that's a much better tool for decision making than just a p value because it connects uncertainty to the actual metrics of interest.
So actually, my comment was based on so do you have any like I don't know, like I don't know what's the right balance between statistics is a whole field in itself.
Yeah.
But as a computer scientist, as like an ML engineer, I have to sometimes use statistics, and when I do, I go on the internet and I try to find an article which tells me how exactly to do this test, and I do it. And like I've been guilty of exactly what you just said right now in the past, where I read up a blog post that said, "Look for statistical significance. If you find it, be good."
Yeah.
But so yeah, I mean, center effort. But yeah, I mean, like I don't want to go through like a full blown statistics course, but I don't want to make stupid decisions.
Yeah.
Because, so,
Yeah. So there's a couple of responses to this. I think at like an organizational level,
right.
organizations should have these kinds of have people with this expertise as
Right.
part of their development. And it's close to, but it's not exactly the same as machine learning, like machine learning skills and machine learning capabilities. Um, but that doesn't help if you don't have that in your organization. So like, and consulting is expensive and not always the right choice. One thing I would say is that traditional statistics from like 1920 to 1990 or so is a bad fit for the skill set of ML folks. It's this very rarefied skill set around recognizing specific patterns of distributions that have nice analytical forms, whether that's like t-testing or chi-square testing or whatever. And it's just like not a great fit for software engineers. It's not the way that like programmers think. And I think that computational Bayesian methods and bootstrapping methods are the two ways that best map onto the way computationally minded people tend to think about their problems. So quick and dirty solution is bootstrapping. Learn to grok bootstrapping and know how to apply it to your particular problem. Like PyTorch Lightning, I found out recently actually has built bootstrapping into their metrics, which is cool. You can actually bootstrap in PyTorch now. And that's like low effort, like conceptually very simple and clean, and will get you like better answers than p-values. If you really want to get good at this, I think that probabilistic programming and computational Bayesian methods fit really nicely with the way computationally minded people think and get you like best in class possible solutions here. And so I think you may even find that some of these Bayesian methods outperform the like less structured ML, like maximum likelihood ML methods that people prefer, or that people tend to use, like trees or neural networks. And so I think I respectful of the fact that people don't have time to learn literally everything, but just a plug for Bayesian methods and probabilistic programming and Bayesian methods for hackers is a great resource. Like it's more like a boot camp than a college course, and a great way to learn that stuff.
Hey, Amon, so you either have the expert, as Charles said, you bring in the expert, or you bring in the expert to check it out. If you don't have that, then and you can't learn everything, then you bring in all the relevant stakeholders in the decision you're trying to make, all the part people, and you just lay out the facts and you let everyone see it, and if everyone agrees, that's a group decision. And if it's the wrong decision in the end, everyone saw the data and they all went with it. So it doesn't all rely on you.
Mm.
Right.
That's the
I
way.
mean,
That's the way
yeah,
I
I guess
approach it. It is significant. You let everyone see it, and then maybe they know something, or they're gonna hire someone to help you out because it's so important.
right. Yeah, I think it makes sense in general, but I guess it has that Donald Rumsfeld problem of unknown. Like if I don't even know that I'm missing something, how do I point it out? So like,
Yeah,
you can't show everything to everyone. You still have to like filter it down to some
yeah,
things that you think.
yeah. I mean, that's just a common engineering problem. So you just bring in as many experts as you can reasonably, and then it's a group decision, or someone at the program level is going to make the call.
Right.
And then there's a risk register. If it's a big program, they have a risk register and they'll just list it down as a risk and then they'll allocate some funds to it. They're like, okay, there's this risk and we're going to put X amount of money to address this risk if it comes up later. And they put a mitigation plan into the overall plan.
That's a great point, Daniel. I think, yeah, my since I'm more of a like academic and small startup person, my emphasis is to just do things with one person rather than thinking at the organizational level. So it's a great helpful perspective. Also, sorry, it is a little bit after 10, so gonna have to cut off at least the recorded discussion now. So thanks everybody for coming, and thanks everybody watching on YouTube. Hope to see you next time.